Today we're going to talk about electron configuration and orbital notation. Now there are two ways chemists illustrate the arrangement of electrons around an atom: electron configuration and orbital notation. An electron configuration consists of symbols that contain three pieces of information. The first piece is the principal quantum number. You can think of this as the first main energy level or shell, like the first energy level or the second or the third and so forth. The second letter indicates the orbital type. For example, if it's an S or a P or a D or an F, there is a superscript that designates the number of electrons in that particular subshell. An orbital diagram looks a little different. It's a pictorial representation of the electron configuration. Each energy level has one or more clusters of boxes. There are clusters of boxes that represent subshells, and each individual box represents an orbital. The electrons are represented by up and down arrows. When we're trying to determine how to write our notations, there are a few rules that we need to follow. The first one is the Aufbau principle, which means building up. As we build up an atom, for example, when we move from hydrogen to helium to lithium, etc., and we're adding more electrons to it, we have to fill the orbitals that have the lowest energy first. The Aufbau principle can be represented in a couple of different ways. One of them looks like this. On the y-axis, we have the energy level, and energy increases as you move from bottom to top. To the right of it, you can see we have a bunch of different lines, and these represent the different orbitals. The s orbitals are in the column on the left. Just to the right of that are the p orbitals and then the d orbitals, and we could go all the way to f orbitals, but we're not going to have to go that far in this class. As we put electrons in, we start at the bottom and then we move our way upward and put them in the order of energy level. For example, we'll put in the 1s electrons first, and then the 2s, and then the 2p, because those are in the next higher energy level. Then the 3s, then the 3p, and then things start to get a little different, because instead of going right to the 3d, it turns out that the 4s orbital is lower in energy than the 3d orbitals are. So we put our electrons in 4s before we put them in 3d. Then 4p, and then we go to 5s before we go to 4d, and that just has to do with how these energy levels are with respect to each other. We go from lowest energy to highest energy. This chart is also often used to illustrate the Aufbau principle and the filling order. As you can see, we have these arrows going from the upper right to the lower left, and you fill in order from top to bottom: 1s, 2s, 2p, 3s, 3p, 4s, etc. Just another handy tool for reminding us how to fill these. The second rule we need to follow is known as the Pauli exclusion principle. This rule states that no two electrons can have the same four quantum numbers. No two electrons can have the same address. When two electrons occupy the same orbital, each electron must have a different spin. And you'll notice it in this particular chart, how we have those up arrows and down arrows. The up and down is to signify that these electrons have a different spin. The third rule is called Hund's rule, and I'll show you how to use that in just a minute. So let's see how this works. We're going to start by writing the electron configuration and orbital notation for our hydrogen and helium in the first row. Now for hydrogen, we have one electron, and looking at this chart, we see that the 1s orbital is going to be the lowest energy. So we are going to write our electron configuration as 1s1. For our orbital notation, we are going to write a single arrow in the upward direction in the 1s orbital. Now let's take a look at helium, where we have 2 electrons. Both of these are going to be in 1s, but because of Pauli exclusion, they have to have different spins. We're going to write our electron configuration as 1s2, but when we do our orbital notation, we will have 1 up arrow and 1 down arrow in that 1s box. So we've just finished our first row of the periodic table. Now, let's go to the second row where we have lithium. Lithium has 3 electrons. We've already filled up our 1s orbital, so we're going to have to go to the next highest energy one, which is going to be the 2s. Our electron configuration will be 1s2, 2s1, and our orbital notation will have an up-down in the 1s, just like helium did, and then we'll add another arrow to the 2s. For beryllium, we have 4 electrons. We're going to have 1s2, 2s2, then we'll have an up arrow and down arrow in the 1s box, and an up arrow and down arrow in the 2s box. Now it's time to add another electron and create boron. Looking at our Aufbau chart, we see that the 2p orbitals are the next ones in line. Boron's going to have a 1s2, 2s2, 2p1, and for our orbital notation, we're going to have an up-down in the 1s, an up-down in 2s, and we'll put a single electron into the 2p orbital. Now's when we have to bring out Hund's rule, because there is a certain way we must fill these. According to Hund's rule, the lowest energy configuration for an atom is the one that has the maximum number of unpaired electrons in the degenerate, same, energy orbitals. So what this is saying, when we get to the p subshell, we have 3p orbitals in there. Electrons repel each other. They don't like to be near each other. So the atom is going to be much more stable if you can put the electrons in different orbitals with the spins pointing in the same direction. We're not going to double up electrons until we have to. Okay, next is carbon. Carbon has 6 electrons, so we will have 1s2, 2s2, 2p2, but we have to follow Hund's rule when we make our orbital notation. So we're going to have an up-down in the 1s, an up-down in the 2s, but we're going to put 1 electron in the first p orbital and 1 electron in the second p orbital. Their spins will be in the same direction. Let's go on to nitrogen with 7 electrons. Our electron configuration is 1s2, 2s2, 2p3. Our orbital notation has 2 electrons in the 1s, 2 electrons in the 2s orbital, but our 3p orbitals each have 1 electron, and the spins are all pointing up. Now let's go to oxygen with 8 electrons. Electron configuration is 1s2, 2s2, 2p4. And for our orbital notation, we have 2 electrons in 1s, 2 electrons in 2s, and we have 4 p electrons. We're now going to have to double up. So we'll put our extra electron, we'll buddy that up in the first p orbital. Now on to fluorine with 9 electrons, 1s2, 2s2, 2p5. Our 1s has 2 electrons, our 2s has 2 electrons, and 2 of our p orbitals have 2 electrons in them, and then the last p orbital has only 1 electron in it. Finally, in this row is neon with 10 electrons. Our electron configuration is 1s2, 2s2, 2p6, and our orbital notation shows 2 electrons in the 1s orbital, 2 in the 2s orbital, and 2 electrons in each of the 2p orbitals. We have just finished the second row of the periodic table. Now, when we get to the third row, things are similar. We go to our little Aufbau table and we see that the next lowest available energy is going to be the 3s. So we will need to put our next electron into 3s. For sodium, we have 11 electrons. Our electron configuration is 1s2, 2s2, 2p6, 3s1. For our orbital notation, we have 2 electrons in 1s, 2 electrons in 2s, 2 electrons in each of the 3 2p orbitals, and 1 electron in 3s. For magnesium, with 12 electrons, our electron configuration is 1s2, 2s2, 2p6, 3s2, and with our orbital notation, 1s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons, 2 of them in each of the p orbitals, and 3s has 2 electrons, 1 up and 1 down. Now we take a look at our little Aufbau chart, and then we see that the next highest energy level are the 3p's. And you should start seeing a pattern. Electron configuration, 1s2, 2s2, 2p6, 3s2, and 3p1. For our orbital notation, our 1s, 2s, and 2p orbitals are all filled. Our 3s is filled, so we need to start filling the 3p's, and we'll have 1 electron in the first 3p orbital. Silicon has 14 electrons. Our electron configuration, 1s2, 2s2, 2p6, 3s2, 3p2. When we look at our orbital notation, we see that the 1s, 2s, and 2p and 3s orbitals are all filled, and we need to follow Hund's rule. And when we add our last 2 electrons, they must go into separate 3p orbitals. We'll move on to phosphorus, which has 15 electrons. Our electron configuration is 1s2, 2s2, 2p6, 3s2, 3p3. And with our orbital notation, our 1s, 2s, 3p, and 3s orbitals are all filled. And because of Hund's rule, when the next 3 electrons go in, they're going to go into separate orbitals to maximize stability. Now we go to sulfur, and that has 16 electrons. Our electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p4. We notice for our orbital notation, we have 1s electrons that are filled, 2s is filled, 2p is filled, 3s, and when we get to the 3p, we have to start doubling up. Chlorine is going to follow a very similar pattern, where 1s2, 2s2, 2p6, 3s2, and 3p5, and our 1s and 2s and 2p and 3s orbitals are all filled, and we fill our 3p orbitals, and there is 1 space left, and that is going to be filled with argon, which has 18 electrons. And I think you can see the pattern here. All of the orbitals are now filled, and we are at the end of our 3rd row. When we get to the 4th and 5th rows, things get a little bit more complicated. Let's take a look at our energy level chart. We will see that after the 3p's, the 4s comes before the 3d's. So electrons are going to go in the outer valence orbital, and then as new electrons are added, they're going to be put into the 3d orbital, which is actually an inner orbital belonging to the 3rd shell. So let's see how this works for potassium, which has 19 electrons. Well, potassium's not too bad. We have 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1. Notice that we are filling the s's before we go back to the 3d's. And you can see that in the orbital notation. Now let's look at calcium, which has 20 electrons. 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. And our electron configuration shows this. But when we get to scandium, we have to start going back and filling in the 3Ds. In titanium, we put another electron in the 3D orbital. And in vanadium, we do the same, and we put a third electron into the 3D orbital. But now we get to chromium, and we get some exceptions. It turns out that the d orbital is most stable when it is either half full with one up electron in each orbital, or when it's full with 2 electrons in each orbital. So when we get to chromium, instead of having 4 electrons in the 3D orbitals, it promotes one of its s electrons so that it can have 5 half-filled orbitals. And this makes it really, really stable. But when we get back to manganese, the extra electron goes back into 4s, and we also have that half-full 3D subshell. We can see how this trend progresses for iron, for cobalt, and for nickel. But when we get to copper, that's another one of these exceptions. Copper promotes one of its 4s electrons to the d orbitals so that it can have a full 3D subshell. And by the time we get to zinc, all of the orbitals up through 3d6 are filled. And then we would go on to start filling the 4p orbitals. We have a similar pattern once we get to the next row, and the f orbitals also fill in an interesting way, but we don't have to deal with that in this class. Now, I wanted to point out that you may see electron configurations in a couple different ways. Some people prefer to put the 4s orbitals before the 3D orbitals, and some prefer to put them after the 3D orbitals, even though they were filled first. And this is because the 4s electrons are valence electrons. The 3D electrons are core electrons. Now let's quickly talk about noble gas notation. Noble gas notation is an abbreviated way to write electron configurations. Noble gases are special because they have a full octet in their valence shell. In order to use noble gas notation, what we do is we put the symbol for the noble gas that immediately precedes the element that we're looking at. We put that noble gas in brackets, and then we write the rest of the electron configuration just as we would if we had written the complete configuration. And here is an example of the regular electron configuration for manganese, followed by the noble gas configuration. Argon is the next lowest noble gas, so that is in parentheses. And here are some other examples of how you could write noble gas notation. So let's summarize. Today we talked about electron configurations and orbital notation diagrams. We also talked about how we have to follow the Aufbau principle and how electrons go in order from lowest energy to highest energy. We also talked about the Pauli exclusion principle, which states that no 2 electrons can have the same address. If electrons are in the same orbital, they must have different spins. We also talked about Hund's rule, which applies in p orbitals, d orbitals, and f orbitals. In order to minimize electron repulsion, the electrons go in different orbitals, and you only double up when you have to. And we have talked about noble gas notation, which is a shorthand way of writing electron configurations.